Hi everybody, and welcome to our module on clustering. Clustering can have many different uses. Imagine if you have a data set that does not have a class attribute or does not have labels. How do you determine what could be a possible good class attribute? Well, you're going to have to find ways to segment the data into specific groups. How do you do that? By looking at each tuple and cross-referencing each tuple and each attribute or characteristic of each tuple with the attributes and characteristics of other tuples in order to determine, are there any natural groupings within your data? This is exactly what clustering does. Cluster analysis means finding similarities between data according to the characteristics found within the data. That also makes cluster analysis exploratory. It also makes it unsupervised. In classification, which we classified as supervised learning, we know what the class attribute is, and we know what the categories or what the labels or what the levels are within that class attribute. In cluster analysis, we don't know that because we don't have a class attribute. And as we know, in data mining, you never use just one method by itself. Clustering has a number of uses that makes it a very powerful complement to all the classification algorithms that we have learned about so far in this course. For example, we can use clustering for data reduction during pre-processing. We can also use clustering for hypothesis generation and testing to identify specific groupings in data and apply our predictive capabilities to those groupings. Or we could use clustering in order to determine the k-nearest neighbors, and specifically, we use clustering to detect outliers. This is very important when we talk about data mining and security. In the yellow box to the right side of this slide, you will find a number of really practical applications of clustering. As we already said, a clustering algorithm is designed to find natural groups of components or data based on any kind of similarity that this algorithm discovers within these data. This also means that the goal for our clustering algorithm is twofold. The first goal for a clustering algorithm is to find clusters in which the data points are as close together as possible. We call this minimizing the intra-cluster distances. The second goal for a clustering algorithm is to segment or partition clusters cleanly from one another by determining which endpoints of our clusters here are as far away as possible from one another. We call this maximizing the inter-cluster distances. But then, really, clusters are in the eye of the beholder, right? Look at this data space here. How many clusters do we have here? Do we have 2? Or maybe we have 6? Or perhaps 4? So as you can already see, clustering is really not all that unsupervised in that we probably already know how many clusters we want to discover, or we can evaluate what the optimal number of clusters are that we can ask an algorithm to discover. To help us identify the optimal number and shape of clusters in our data set, we employ different types of clustering algorithms. First, we have partitional clustering algorithms like k-means or k-medoids. K-means and k-medoids divide our data objects into non-overlapping clusters in which each data object is in exactly one subset. So here we have clean subsets and clean partitions. Hierarchical clustering, on the other hand, allows us to discover clusters inside of clusters inside of clusters. Typical methods for that are Diana and Agnes, both of which we will discuss later. And lastly, we have density-based clustering. Density-based clustering groups together points that are very dense, in other words, that are closely packed together, and it marks as outliers anything that is outside of a specific density radius. A typical method for that is dbScan, which we will also discuss later. So what can we expect from a good clustering algorithm? Well, first of all, we want our clustering algorithm to be scalable, which means we really want it to analyze all the data in our data sets rather than a sample, which is what we used in a pinch for our classification. We also want our clustering algorithm to be able to deal with all types of attributes, not just numeric, but numeric and nominal and categorical and all of those, right? We also want to be sure that our clustering algorithm can find clusters with arbitrary shapes and that it can process more than 4 or 5 attributes, but that it can really deal with high dimensionality, that is 20, 30, 40, 50 attributes, right? So the goal for our good clustering algorithm then will be to find high quality clusters where we have high intra-cluster similarity and low inter-cluster similarity. And when we talk about similarity, of course, we have to talk about one concept that we already know from the very beginning of our journey into data mining, namely distance. Distance calculations are at the heart of clustering. We have different ways in which we can calculate distance. Let's say we have these two clusters here. We have the option of computing single link distance. Single link distance demarcates the smallest distance between an element in one cluster and an element in another cluster, so it's a minimum distance. And that's in contrast to the complete link, in which we calculate the maximum distance between one element in one cluster and an element in another cluster. We can also calculate the group averages, that is the average distance, that's what we call the average link, or, and this is one of the most popular method, we can calculate the centers of each cluster, either with a mathematical calculation, that's when we call it a centroid, or by looking for the data point that is closest to the mathematical center of our cluster, and that's what we then call our medoid. A medoid is an actual data point that is as close as possible to our centroid. This also means that distance calculations are going to make a return in this module, specifically, and you guessed it, our Euclidean distance metric. But that's not all. Now we know that our centroid is the middle of a cluster. As such, it is the sum of all data points divided by the number of all data points. We also will want to calculate the radius of our cluster, which is the square root of the average distance from any point of the cluster to its centroid. And since we are calculating our radius, we also will want to understand what the diameter of our cluster is, namely the square root of the average mean squared distance between all pairs of points in our cluster. So to build good clusters, we need to consider how we want to partition our clusters, how we want to separate our clusters, whether we want to allow points to belong to just one cluster or maybe percentage-wise to one cluster and perhaps to another. We want to know and determine what similarity measure we are going to use, what distance measurement we're going to use, Euclidean, Manhattan or so, and we want to understand how we want to use our clustering space, whether we want to really use our full clustering space, that is all of our data, or whether we want to use subsets.